Welcome back to Calculus 3. I'm Dr. Jeff Groh. Today we talk about line integrals. We'll begin by looking at, say, a curve in the plane. Let's suppose this curve has a definite beginning and end. We'll divide the curve up into little segments. Each of these segments will have some length, delta sk. We'll choose sampling points, ck, on each of these little pieces. And here's what we'll do. We'll talk about the integral on the curve. Let's suppose the curve is denoted by c of some function multiplied by an element of arc length. This will be defined by the limit as the norm of the nth partition goes to 0 of the sum, as k goes from 1 to n, of f of ck times delta sk. This is very much like the old Riemann integral, except instead of adding up function values at each point along the x-axis, we're adding up function values that are defined on points along some curve that lies in the plane. So this is a line integral. So how do we actually evaluate these line integrals? Let me give you an example. Suppose I give you the parametric curve t squared, where t takes values in the interval, say, 0 to 1. This gives me a nice little piece of parabola in the plane from 0, 0 to 1, 1. And I'd like to calculate, with my curve defined by this parametric curve, I'd like to integrate the curve, let's say x times y times ds. How do I evaluate this line integral? I'm not asking what it means or how to interpret this in any way, just mechanically, how do we evaluate this line integral? The first thing we need to understand is the element of arc length. You'll recall that the rate of change of arc length with respect to time is the norm of the velocity vector. It's the speed. The speed. That means then that the element of arc length is the norm of dr dt times dt. And that's exactly how we'll calculate the element of arc length. In this case, dr dt is 1 to t, which means that the speed ds dt is the norm. It's the square root of 1 plus 4t squared. That means the element of arc length is the square root of 1 plus 4t squared times dt. It follows then that this integral can be calculated as, if this is our integral I, it'll be the integral from 0 to 1, x times y, that's t times t squared, times ds, which is the square root of 1 plus 4t squared times dt. I'd like to point out that what we are doing is evaluating the integrand on the parametric curve. And this yields this definite integral. To evaluate the integral, we'll require a u substitution. I see the t lying around, so I'll divide the 8 off. Also note, we can solve for t squared. T squared will be u minus 1 divided by 4. The integral I will then transform. When t t is 0, u is 1. When t is 1, u is 5. The t dt becomes 1/8 du, and then we'll have, that takes care of the t dt. We still have t squared, that's u minus 1 over 4, and then u to the 1/2 du. 4 times 8 is 32. We'll distribute u to the 1/2. We'll have u to the 3/2 minus u to the 1/2 du. We have then 1 over 32 times u to the 5/2 times 2/5 minus 2/3 u to the 3/2 evaluated from 1 to 5. The 2 can come out, canceling with the 32 to leave a 1 over 16. Plugging in 5, we'll have 5 to the 5/2. Remember, if you have something to the 5/2, that's something squared times the square root of that something. So we'll have 25 divided by 5. We'll have 5 root 5 minus 1/3, and when we have something to the 3/2, we get that something root something. So we end up with 1/3 times 5 root 5 minus what we get when we plug in the 1. That's 1/5 minus 1/3. We have then 1/16. One of them minus 1/3 of them is 2/3 of them. That'll give us 10/3 root 5. 3 minus 5 is negative 2/15 times a negative, you get plus 2/15. Let's leave it at that. Let's do another example. Let's evaluate the integral on a curve of x ds, where the curve is described as follows. We'll start at the origin and go along the curve y equals x squared to the point 1, 1. And then we'll go back along y equals x to the origin. This will give us a closed loop. It is appropriate when integrating on a closed loop to put a little circle around these little line integrals, indicating we're going on a closed path. Though the use of the circle is not necessary, it is optional. We can break the path into two pieces. There's curve 1 and curve 2, because this curve is piecewise smooth. We'll parameterize curve 1 first. That will be the curve where x is t, y is t squared. And t runs from 0 to 1. On curve 2, we can parameterize this two different ways. Technically, the curve starts at 1, 1 and ends at 0, 0. We should write 1 minus t, where t runs from 0 to 1. That would be a parameterization of this curve. At t equals 0, we are at the point 1, 1. At t equals 1, we're at the point 0, 0. And y and x are equal. Y equals x. To integrate on curve 1, x ds, we need to calculate the speed. First of all, our dot will be 1 to t, so that we will have the integral from 0 to 1. X on this curve is t, and then ds will be the square root of 1 plus 4t squared dt. If we set u equal to 1 plus 4t squared, du will be 8t dt. We'll divide the 8 off. the integral becomes the integral from 1 to 5. And then we get 1/8 u to the 1/2 du. This gives us 1/8 times 2/3 u to the 3/2 evaluated from 1 to 5. Or 1/12 times 5√5 minus 1. That's the integral on the first piece. Now we have to do the integral on the second piece. On C2, r dot is -1 minus 1. So we'll integrate from 0 to 1, x, which is 1 minus t, times the speed, which is the square root of 2 times dt. We have then the square root of 2 times t minus t squared over 2 evaluated from 0 to 1, which is root 2 times 1 minus a half is a half, and then subtract 0. We get root 2 over 2. The total then, the integral along the whole curve, integral of x ds, is the sum of these two results, 1/12 5√5 minus 1 plus root 2 over 2. I wanted to point something out, however. Consider the integral on C2 that we found here, root 2 over 2. We had a particular parameterization. I want to try a different parameterization. Suppose for C2 we had made the following parameterization. Now, technically, this gives us the parameterization going in the wrong direction. I ask, does it make a difference? Keep in mind that ds is the norm of dr dt times dt. The norm. The norm is non-negative no matter what. If you parameterize in one direction, the tangent vector will go one way. If you parameterize it in the other direction, the tangent vector will go in the other way. But the norm can't detect the direction the vector goes, only its magnitude. Let's see if it makes a difference. We'll calculate r dot, which is 1, 1, so that the norm of r dot is still the square root of 2. The integral on C2 of x ds will be the integral from 0 to 1 of x, which we know now to be t, times root 2 dt. When we integrate, we'll get root 2 times t squared over 2 evaluated from 0 to 1. And that, again, is root 2 divided by 2. It didn't make any difference parameterizing one way versus the other. As long as the infinitesimal is the element of arc length, it doesn't matter what direction we parameterize the curve on. It will make a difference in other sorts of line integrals that we are about to encounter. Here's an example. Find the mass of the spring along the helix cosine t, sine t, t. We'll have t go between 0 and 6 pi. So we have 3 turns on the helix. Where the density is given by rho equals, say, 2 plus z. We'll start with a density of 2 when z is 0, and then the density will increase linearly as we go up on the spring. So we want to find the total mass. Mass, as you know, is the integral of density. What we'll do is we'll have density, a linear density, since this is along a path. We'll have units of kilograms per meter. If we multiply that by elements of arc length, which has units of meters, we'll have kilograms per meter times meters, which is kilograms. We'll add that up as we move along the curve, and that will give us the total mass. In order to find the element of arc length, we need first to find the velocity vector. That's going to be minus sine t cosine t 1. The speed then, the element of arc length, will be the norm of the velocity times the element in t. That's going to be the square root of sine squared plus cosine squared plus 1 all times dt. That's the square root of 2 times dt. We need to now evaluate this integral along the curve where z is equal to t. The total mass will be the integral from 0 to 6 pi. We'll evaluate the density on the curve. On the curve, z is equal to t. The element of arc length is the square root of 2 times dt. We have root 2, 2t plus t squared over 2 evaluated from 0 to 6 pi. That's root 2 times 12 pi plus 36 divided by 2. That's 18 pi squared and then minus 0. We'll leave it at that. I want to discuss a different kind of line integral, this time integrating on a curve some function of position times, let's say, a little differential dx. In this case, let's look at a specific example. In particular, suppose we're integrating on a curve y dx, and the curve is a straight line segment from 0, 0 to 1, 2. The curve C can be parameterized as follows. T, 2t, where t takes values between 0 and 1. That way when t is 0, you're at 0, 0, the origin. And when t is 1, you're at the point 1, 2. We'll also parameterize this in the other way after we do this to see if the results compare. Here we'll have the integral from 0 to 1. Y along the curve is 2t, and dx will be 1 times dt. If x is equal to t, dx is 1 times dt. That's just t squared evaluated from 0 to 1, which gives us 1. Let's look at the curve parameterized in the other direction. Let's denote that by minus c. Whenever we have a curve parameterized one way, and then parameterize it in the opposite way, let's denote that by minus c. In this case, we can parameterize the curve still along the line y equals 2x as 1 minus t, 2 times the quantity, 1 minus t. T will take values between 0 and 1. When t is equal to 0, we're at the point 1, 2. When t is equal to 1, we're at 0, 0. You can see that the integral along minus c of y dx will be the integral from 0 to 1. Y in this case is 2 times 1 minus t, and then dx. dx will be negative 1 times dt. Distributing the -2, we'll have -2 plus 2t to integrate. This gives us -2t plus t squared evaluated from 0 to 1. Plugging in 1, we get -2 plus 1, which is -1. And then, of course, subtracting 0, the answer is -1. Notice the change in sign by changing the orientation along the curve. Going from 0, 0 to 1, 2, we had a positive 1 result. Going from 1, 2 to 0, 0, we have a -1 that results. By switching the orientation, what you're doing, if you have some function times dx, as you march from this direction from 0, 0 to 1, 2, all the little changes in x are positive. When you go the other way from 1, 2 to 0, 0, the changes in x change sign. And that's what changes the sign. It doesn't change the magnitude of the result. It only changes the sign. That doesn't happen for ds, because ds, a little change in arc length, will be positive whichever way you go because of that norm. We have the following theorem. Let C be a piecewise smooth curve with a given orientation. Let minus C be the same curve with opposite orientation. Then if we were to integrate along C, m dx plus n dy plus p dz, you'll get the opposite if you integrate on the curve having the opposite orientation. M dx plus n dy plus p dz. You can move the minus over here if you wish. You can see that changing the orientation on the curve gives you the opposite sign. You'll recall from earlier in the course that work is force dot displacement. That only works if you have a constant force with a specific vectorial displacement. What if the displacement is along some curve? If the force is acting at some point along this curve, you get a little vectorial displacement. We'll call that dr. We'll slice up the little displacements into little segments as we move around the curve of infinitesimal length. It follows then that the amount of work done in making a little infinitesimal displacement is an element of work equal to the force evaluated at this point dotted with this infinitesimal displacement. The little change in r is always equal to a little change in x, a little change in y, and a little change in z. If the force F has components m, n, p, then this little tiny element of work will have the form m dx plus n dy plus p dz. To get the total work done, you have to integrate to add these up along the whole curve. The total work is the integral along the curve of the force dotted with the infinitesimal displacement. This is your new work formula. It allows for a variable force. Force doesn't have to be the same, it could be different at different places. And we have little infinitesimal displacements allowing the displacement to occur along an arbitrary path. As an example, let's find how much work is done by the force field minus 1/2 x minus 1/2 y 1/4 in moving an object along the path cosine t, sine t, t. Do you remember what this kind of path is called? That's a helix. We'll let that be denoted by the curve C. The total work is going to be the integral along C of f dot dr. Let's calculate that. First, let's write the work as the integral on C of f dot dr. Remember, dr is always the vector dx, dy, dz. That'll give us minus 1/2 x dx minus 1/2 y dy plus 1/4 dz. We'll now evaluate this along the path. I forgot to say, we'll have t go from 0 to, let's say, 3 pi, 1.5 times around that loop along the helix. 1.5 times around the helix. We'll have the integral from 0 to 3 pi minus 1/2 x, which is cosine t, dx. If x is cosine t, then dx is minus sine t times dt, minus 1/2 y times dy, which is cosine t dt, and then plus 1/4 times dz. dz is dt. You can see that the first two terms will cancel each other out. We'll have 1/4 times 3 pi, or 3 pi over 4 is the total work done in moving this object 1.5 times around this helix with the given force. In our next example, I'd like to integrate along a curve. Let's do y dx plus x squared dy. And the curve is going to be from y equals 4x minus x squared. This is a parabola opening down. You can factor to get x times 4 minus x to see that the intercepts are 0 and 4. And I want to go from the point 4, 0 to the point 1, 3 on this curve in this direction. So the curve needs to be specified with an orientation for these sorts of integrals, because the direction you go will determine the sign of the dx and the sign of the dy. We'll parameterize minus c, however, just because it's easier. Let's compare the two. Minus c is t 4t minus t squared. If I wanted to parameterize c, I could do it this way. I could take 4 minus t, where t goes from 4, where t goes from 0 to 3. On the first one, t goes from 1 to 4, from 1 to 4 on the x. Here you'll have to have 4 times 4 minus t minus 4 minus t squared, and t will run from 0 to 3. I don't know about you, but I kind of like this parameterization better. The only thing is it has the wrong orientation, but we can fix that by, instead of integrating c, we can put minus the integral of minus c. On this curve, y is 4t minus t squared, and dx is dt. X squared will be t squared, and dy will be 4 minus 2t all times dt. We'll combine like terms before we begin, and we'll also distribute the negative. Here we'll have a negative 2t cubed times a negative gives us 2t cubed. We'll have a 4t squared minus t squared is 3t squared, but then we get a minus. And then we have left over a minus 4t all times dt. Integrating, we'll have t to the fourth over 4 canceling the 2 leaves us with t to the fourth divided by 2 minus t cubed minus 2t squared, evaluated from 1 to 4. Plugging in 4. 4 squared is 16. 16 squared is 256 divided by 2 is 128. 4 to the third power is 64. T squared, 4 squared is 16 minus 2 is minus 32. Minus what you get when you plug in 1. That's 1/2 minus 1 minus 2. 128 minus 64 is 64. 64 minus 32 is 32. How many halves is that? 64 halves minus 1/2 plus 3. 3 is 6 halves. We'll have 70 halves minus 1/2 is 69 halves. In our next example, let's integrate on c y cubed dx plus x cubed plus 3xy squared dy. And we'll suppose that the curve is given by the following parameterization. It's 3 cosine t, 3 sine t, where t goes from 0 to 2 pi. In other words, the curve is a circle of radius 3, going counterclockwise about the origin. The integral becomes the integral from 0 to 2 pi, y cubed. 3 cubed is 27. We'll have sine cubed of t times dx. dx will be minus 3 sine t dt. And then we'll have plus the quantity x cubed. I'll write that as 27 cosine cubed plus 3 times 3 cosine times 9 sine squared, all times dy. dy is 3 cosine dt. 27 times 9 is 81. We'll have an integral from 0 to 2 pi, negative 81 sine to the fourth. When we distribute, we'll have an 81 cosine to the fourth. We'll have 3 times 3 is 9, times 9 is 81, times 3 is 243. So we'll have plus 243 cosine squared sine squared. all times dt. We may, of course, factor 81 out of the whole thing. Now, how do we deal with the negative sine to the fourth plus cosine to the fourth? We can think of that as a difference of squares. Cosine squared minus sine squared times cosine squared plus sine squared. And that's 1. Plus 3 times cosine squared sine squared all times dt. Now cosine squared minus sine squared. That's a double angle identity. That's cosine of 2t. Keep in mind that sine of 2t is twice sine of t cosine of t. We'll divide this 2 over here. 2's do not cancel because the 2 in front of the t is inside of the sine function. And the sine function is a terrible monster doing horrible things to this 2. So you can't get it out of the mouth of the monster to cancel. We'll have 81 integral from 0 to 2 pi cosine of 2t plus, now we have a square. We're going to have 3/4 of sine squared of 2t all times dt. Now, the period of cosine 2t is pi. And we are integrating over 2 periods. So the first term should contribute nothing to the answer. The second term will contribute something, and there we need to use a half angle identity. Sine squared theta is 1/2 times 1 minus cosine 2 theta. 3 times 81 is 243. We have this 4 coming out, but it's going to be hit by another 2. So we'll write that as 8, integral from 0 to 2 pi. We'll convert the sine squared. We'll have 1 minus the cosine of 4t. Of course, the period is 2 pi over 4, which is pi over 2. We're integrating over 4 periods, so we get quadruply nothing. Integrating, we'll have 2 pi times 243 over 8. Canceling, we get 243 pi over 4. I'd like to introduce to you the fundamental theorem of line integrals. And it goes like this. Suppose f is, say, continuous. C0 functions are continuous functions. And we want continuity to be in some open set that contains the curve that we're integrating on. And conservative. Do you remember what it means for a vector field to be conservative? It's equal to the gradient of some scalar potential. Let's let little f be the potential function. We're going to let C be a curve from the point A to the point B. Then the integral on that curve of f dot dr, that's the amount of work done by this force in moving the curve from point A to point B along the curve, will be the potential function evaluated at B minus the potential function evaluated at A. This curve has some very interesting implications. If this is my point A and this is my point B, the amount of work done does not depend upon which path I take in getting there. I can take different paths. The only thing that matters is Do I start at A and end at B? I'll evaluate the potential function at the endpoints and subtract. This gives us a kind of path independence for integrals involving conservative vector fields, like gravity, for instance. Also, if the curve is a closed loop, beginning and ending at the same place, then A and B are equal, and the integral for the work done will be 0. Consider this. If I'm dealing with gravity, which I know to be a conservative vector field, around, say, the Earth, and I'm monitoring a satellite that perhaps is in a highly elliptical orbit, maybe a tundra orbit, for instance, then no matter how elliptical that orbit, the amount of work done by the gravitational field on that satellite in one complete orbit is 0. No work is done. No net work is done. It might take some work to push this thing up. It might release some energy coming down. There's 0 net work in one complete orbit. This will be a very interesting theorem, but we need to prove this. So, proof. Suppose F is a gradient field. That means the coordinates are df dx, df dy. We can do this in the plane. This works in space, it works in arbitrary dimensions. The proof works out pretty much the same. And let's suppose C is determined by R of t equals x of t, y of t. T will take values between t0 and t final. Note that R of t0 is assumed to be the point A, and R of t final is assumed to be the point B. The work done will be the integral along this curve of df dx times dx plus df dy times dy, because you'll remember dr is the vector dx dy. The integral becomes the integral from t0 to t final of df dx dx dt plus df dy dy dt all times dt. But by the chain rule, that's the integral from t0 to t final of the derivative with respect to time of the quantity f of x of t, y of t, dt. This is now an integral of the type from Calculus 1. The integral of the derivative, well, the antiderivative of the derivative is just the original function. We get f evaluated at tf. X and y evaluated at t final gives you the terminal point B. F evaluated at t0 gives you the initial point A. And that's the end of the proof. As an example, our first prototype is xy. Its potential function was x squared over 2 plus y squared over 2. Let's have this go along a straight line from, say, 0, 1 to 2, 4. What is the equation of that line? We need a parametrization of this path. Actually, we don't. To calculate the total work done along that path, all we have to do is evaluate the potential function at the endpoints and subtract. Evaluating at 2, 2 squared is 4 divided by 2 is 2. 4 squared is 16 divided by 2 is 8. 0 plus a half. We get 10, which is 20 halves, minus 1 half is 19 halves. Now I want to give you an example. Suppose I'm integrating on a closed loop, just dx. What should I get? There's a couple ways to view this. If c is just some closed path, then I'm adding up changes in x all the way around the curve. On some portions, the changes in x will be positive. On other portions, the changes in x will be negative. If I go completely around this closed loop, the net change in x should be 0, no matter what closed loop you're working with. There is another way to see this. Consider the vector field 1, 0, and let's let dr be dx, dy. The work done in moving this along any curve is going to be just dx. But I ask you, is this vector field conservative? We can tell. The test was my equals nx. My is 0 and nx is 0. And so the answer is definitively yes. This vector field is conservative, which means that if you integrate on a closed loop, you get the potential function evaluated at the endpoints and subtracted, but the endpoints are the same. So the interval on any closed loop will be 0. So you can see that here. I'd like to extend that application to integrals of the form x to the n dx. In this case, you can see the vector field will be x to the n 0, and of course, dr is dx dy. Is this conservative? My is the derivative of x to the n with respect to y, and that's 0. The derivative of the n component with respect to x is also 0. So the answer is yes. Because this vector field is conservative, if you integrate on any closed loop, by the fundamental theorem of line integrals, you must get 0, no matter what that closed loop is. I want to extend this example even further. In this case, my vector field is of the form an arbitrary function of x, 0. When I take the dot product, I get f of x dx. Again, I'm assuming that the path is a closed loop. Is this conservative? The derivative of the n component with respect to y is 0. And of course, the derivative of the n component is also 0. So the answer is yes. The fundamental theorem of line integrals then tells you that as long as this is a closed loop, no matter what function of x you're dealing with here, you will get 0. This begs the question, what do you get integrating around to some closed loop of y times dx? It seems you must have y's in here in order to get anything at all. Any function of x times dx on a closed loop will give you nothing. So let's look at some arbitrary kidney-shaped lamina and the boundary curve C. Let's orient it in a counterclockwise fashion. Counterclockwise meaning that if you were to stand on the edge and walk, your left arm would always be pointing into the enclosed region. Let's suppose that the curve is closed, but it doesn't do this. It doesn't cross itself like that. It just has a closed nature. We're partitioning these with little increments in x. But we're taking y values times our little increment in x. Y times little dx gives me the area of a little parallelogram. Gives me the area of a little rectangle. So I'll get little positive rectangles as I move to the right. Little positive rectangles. You can see that as I move along the curve here, I'll get the area underneath the region, and it will be positive. But as I go across the top, the little changes in x become negative as we go across the top. Those little areas of these rectangles will be negative. I'll end up with negative areas across the top. And then as we go back forward, we'll have little positive areas. The net area will be what we have in here, but negative. So we get minus the area enclosed by the curve C. Positive areas as you move under, negative areas as you move over the top. The net will be a negative area minus this little positive area. You get the negative of the area of the kidney-shaped lamina. This is really important for us to understand. If we're integrating on a closed loop x dy, what do we get in this case? Let's go back to our generic kidney-shaped lamina. In this case, we're partitioning this along dy's. dy on this side is positive, dy on this side is negative because we're going down as we go on this side. And x times the dy gives us areas of little rectangles. In this case, there'll be negative areas and then positive areas as we go along the other side. The net will be the positive area enclosed by the curve. Positive this time. We have the following theorem. Let's suppose that we have a region R, and the curve is the boundary of the region, and we're going to parameterize this in a counterclockwise fashion. Then we have the following two facts. The integral around the boundary of the region of y dx is minus the area of the region, whereas if we integrate around the boundary of the region x dy, we get positive the area of the region. This gives us a third option. The area of the region can also be described as 1/2 times the integral around the boundary of the region of x dy minus y dx. X dy gives us the area. Y dx would be minus the area, so if we put a minus, we'll get another contribution of the same area. Multiplying by 1/2, we get just the area. Let's use this formula to show a really slick way of calculating the area inside of any ellipse. Consider x squared over a squared plus y squared over b squared equals 1. We can parameterize this in a counterclockwise fashion by setting x to be a cosine of t and y as b sine of t. According to the theorem we just wrote down, we should be able to integrate 1/2 around the boundary of this curve, x dy minus y dx. That would be 1/2 times the integral from 0 to 2 pi. As t goes from 0 to 2 pi, you go all the way around the ellipse. X is a times cosine, dy is b times cosine dt, minus y, that's b times sine, dx will be negative a sine dt. AB is a coefficient of both terms. We can factor that out. All that's left is cosine squared plus sine squared, which is 1. So we get the coefficient AB over 2 times 1 times 2 pi. And the area of the ellipse is pi AB. Now I want you to think about how easy this was in comparison to what you might have done in Calculus 1 or Calculus 2. You might have tried solving the original equation, x squared over a squared plus y squared over b squared equals 1 for y. This will, of course, give you plus or minus b times the square root of 1 minus x squared over a squared. If you integrate the plus part, the top part, you have to multiply by 2. Name the method. You have a difference of squares under a radical. This is a definite trig substitution problem. Yes, this is not so nice as what we just did. We walk away in tears compared to how simple this last computation was. I'm going to introduce two new concepts. The first is called circulation and the second is called flux. First, how do I define circulation? Suppose you have some region R and the curve C is the boundary of the region R, like this. We of course parameterize the boundary so that we go counterclockwise around. Always, if we were walking along the edge, keeping the enclosed region to our left. Let's suppose that you have some vector field that's defined throughout this region. Now, over here along the boundary, you might have one of these vector fields sticking out, something like this. If you have the unit tangent vector, you can project the vector field f onto the tangent vector and get the component of f that goes in the direction of the tangent vector t, the unit tangent vector. How do you project the vector f onto the unit tangent vector t? Well, you take f dot t over norm t squared times t. The coefficient of t will be the component. The norm of t is 1 because it's a unit vector. So to get the component of f in the direction of t, you just take the dot product, f dot t. If we add up around the entire boundary of the region, f dot, that unit tangent vector, times an element of arc length, we get what is defined to be the circulation. It's the tendency of the vector field to go tangent to the curve. If the vector field is at exactly a right angle to the unit tangent vector, the dot product will be 0, and you will not get any circulation at all. If the angle is bigger than 90 degrees, the dot product will be negative, and that gives you a sense of circulation in a clockwise direction instead of a counterclockwise direction. We've defined the circulation to be the integral around some closed loop around the entire boundary of some region of the vector field f dot unit tangent vector times the element of arc length. But we can do better. Remember that t is the derivative of the position vector with respect to arc length. It follows then that the circulation can be calculated as the integral around the boundary of the region of f dot. If I take t and multiply by ds, I just get dr. I'll have f dot dr. Those are the old work integrals. So circulation and work are certainly related in this way. Before proceeding to examples, I want to define the concept of flux. In this case, again, we have some generic kidney-shaped region. The boundary curve is the boundary of the region. It's parameterized in a counterclockwise fashion. If you have some vector field F, we can project onto a unit exterior normal. To get the tendency to go out of the region. How do you calculate such a projection? Again, it's f dot n over the norm of n squared n. The component will be the coefficient. The norm of n is 1 because we've defined it to be a unit exterior normal. The flux will be, by definition, because I said so, the integral around the boundary of the region of f dot n ds. N is a unit exterior normal. Now, we can operationalize this a little better. Let's suppose that our tangent vector is right here. The normal vector will be at a right angle to that and have exactly the same magnitude. You'll remember the tangent vector was dx ds, dy ds. To get the normal vector, notice it will, if t has both positive x and positive y components, the normal vector will have a positive x and a negative y. But to get it, the normal vector will be dy ds negative dx ds. You switch the coordinates and negate one to get one that is at a right angle. When you take the dot product, you will get 0, and it will have a positive x component and a negative y component. That means you can take your integral around the boundary of the region. You'll take your vector field f, mn, but you'll dot it with, if you multiply by ds, dy comma negative dx. And this gives you an easy way of calculating flux. I want to calculate both circulation and flux for our prototypes. First, let's look at the vector field xy. And let's let the region R be the unit disk. The boundary will be the unit circle, parameterized in a counterclockwise fashion. We can parameterize that as cosine t, sine t. Let's calculate the circulation. Remember, this vector field has vectors all pointing out. It's all divergy and not too much curly. So let's see what happens here. We're expecting to get no circulation. We'll integrate around the boundary of the region x dx plus y dy. We've already shown if you have any function of x times dx and you integrate around a closed loop, you must get 0. The same is true if you integrate y dy around a closed loop. And so we are getting absolutely no circulation whatsoever for this vector field. Now let's calculate the flux. We expect a positive flux. We'll have the vector field F dotted with dy, comma, negative dx. We're integrating around the boundary of the region x dy minus y dx, which is twice the area. The area of the unit disk is pi r squared, pi times 1 squared, that's just pi. We get 2 pi units for the flux, a positive flux. A positive flux is called an efflux. A negative flux would be called an influx. Seems that in my bank account the dollars mostly have an efflux character. Now let's look at prototype number 2. Circulation is the integral around the boundary of the region of this function, this vector field minus yx dotted with dx dy. That's going to be the integral around the boundary of the region of minus y dx plus x dy, which again is twice the area, or 2 pi. You'll remember that this vector field tended to go around like this, so it tended to swirl around in a counterclockwise fashion, just like this. The fact that the circulation is positive gives you an indication that the circulation of the vector field is in a counterclockwise direction. Now let's calculate the flux. That's going to be minus yx dotted with dy minus dx. We get the integral around the boundary of the region of minus y dy minus x dx. And since the curve is a closed loop, both of those will contribute nothing, and there will be no flux. Exactly as you might expect for a vector field that's just swirling around and not diverging at all. We've already seen with these two vector fields the divergence and the curl. Now we've seen the circulation and flux. You might anticipate that there should be a relationship between curl and circulation, and that there should be a relationship between divergence and flux. Those relationships will be established in a very important theorem that is coming up called Green's theorem. We've seen that for conservative vector fields, the path you choose in going from point A to point B is irrelevant. To evaluate the path integral of f dot dr along some curve, all you have to do is evaluate the potential function at the endpoints and subtract. This is the fundamental theorem of line integrals. So there's a certain path independence. It doesn't matter which path you take, as long as you start at A and end at B. It turns out that path independence also implies that the vector field is conservative. Let F be continuous on an open set containing the curve C, where C starts at A and ends at B. Then the integral on C of f dot dr is path independent If and only if f is conservative. We already know that if the vector field is conservative, then the work integrals are path independent. We need to be able to prove the other way around, though. In the proof, this direction is where conservative implies path independence, but that's established by the fundamental theorem of line integrals. Suppose the work integral is path independent. Then we have to establish the existence of a potential function making f a gradient field. Let A be the point x naught, y naught. Let's do this in the plane. We can do this in arbitrary dimensions. And B be the point x, y. Let's define a proposed potential function. It's the integral on the curve of f dot dr, where we're allowing the endpoint to be this variable point xy. If f is the vector field Mn, we want to show, and WTS is the standard abbreviation in mathematics for the phrase want to show, that f is the gradient of our potential function. In other words, m is df dx, n is df dy. Let's calculate df dx, which we know to be the limit as h goes to 0 of, we'll write this as f of x comma y minus f of x minus h comma y all over h. We're backing off along the x coordinate. So if we're starting off at x naught, y naught, and ending at xy, what we're doing is we're taking a path that goes to some point directly to the left of xy and then heading directly towards it, holding y constant. In doing so, the change in y will be 0 all along that terminal path. This will give us the limit as h goes to 0. If we subtract these two, we're just integrating on this little tiny piece of path. We have 1 over h, the integral from x minus h to h, and the function will be m of t y dt plus n of t y dy, which we know to be 0 along that last part. It's at this point that we use the mean value theorem for definite integrals from Calculus 1. Do you remember the mean value theorem for definite integrals? The mean value theorem for definite integrals states that a continuous function on a closed and bounded interval attains its average. There's some point C where the height at C is equal to the average height. We can use that here. We'll have the limit as h goes to 0. Now, if you subtract the two limits of integration here, you end up with h. So we have 1 over b minus a out front. There will be some point C where the function m evaluated at c comma y is equal to this average. C must lie between x and x minus h. In the limit as h goes to 0, since C is trapped between x and x minus h, C will get squished to x. Similarly, n will be the partial derivative of f with respect to y. And the proof is over. We now know that path independence and conservative are equivalent concepts. Suppose we have the following theorem. The following are equivalent. 1. F is conservative. 2. Work integrals are path independent. And 3. If you integrate on a closed loop, f dot dr, you get 0. You might not have anticipated that the last one is equivalent to the vector field being conservative, but we'll show that it is. We're assuming that this is true for all closed loops C. For the proof, the equivalence of 1 and 2 is already done. That's the last theorem. Let's prove that 2 implies 3. The way to do that is to take an arbitrary closed loop, C, and break it into two curves, C1 and C2. We know because of property 2 that if we integrate on minus C2, we'll get the same thing if we integrate on C1. Minus C2 is C2 with the opposite orientation. The integral on C1 and minus C2 results from the path independence. If we move this over, we get 0 as the integral on C1 plus the integral on C2. But if you go on C1 followed by C2, that's just the curve C. We deduce then that path independence implies that you get 0 on all closed loops. Let's prove that getting 0 on all closed loops implies path independence as well. We'll assume that you get 0 on all closed loops. Let C1 and C2 be paths from A to B. So C1 goes from A to B, and C2 also goes from A to B. Then, if we integrate on C1 and subtract and add the integral on minus C2, that forms a closed loop, so you must get 0. But the effect of going on minus C2 is minus the integral on C2. If we move this to the other side, we get path independence. The integral on C1 equals the integral on C2. And the theorem is over. In our next example, suppose I wish to evaluate the integral on f dot dr, where f is the vector field y cubed plus 1, followed by and 3xy squared plus 1. The path will be, let's say, semicircle from the origin to the point 3, 0. Now, I don't know about you, but I'd rather not parameterize this path. I'd much rather parameterize the straight line segment between these two. t comma 0 as t goes from 0 to 3. But I don't know if I'll get the same thing on the two different curves until I know I get path independence. And to get that, I need to know whether or not the vector field is conservative. Is it conservative? We have an easy test for whether or not these vector fields are conservative. My is 3y squared, and that is equal to nx. The vector field is conservative, so I can replace my curve C with another curve, C2, parameterized as t comma 0. T goes from 0 to 3. I'll integrate on C2, f dot dr. That's going to be y cubed plus 1 dx plus 3x y squared plus 1 dy. On this curve, dy is 0. dx will be equal to dt. We'll have then the integral from 0 to 3. Y is equal to 0. We'll integrate 1 times dx, and dx is dt. So the answer is 3. There are huge advantages to replacing some crazy curve with maybe some straight line segment. It's much easier to parameterize and easier to integrate too. But we only allow ourselves to do that if the vector field is conservative, and hence the work integrals are path independent. In this case, we were able to easily show that the vector field was in fact conservative. We've been working up to some really big theorems. Next lecture we'll talk about Green's theorem that'll put a lot of these ideas together. It will talk about these path integrals. We'll also bring up flux and circulation, curl and divergence. All of these will be part of Green's theorem.